speaker is Dinghong Zhong, and he's going to be talking about efficient concolic execution for WebAssembly by compilation and snapshot reuse. Please take it away.
Okay, thank you. Thank you for the introduction. Thank you everyone for coming to my talk. And I'm Dinghong from Tufts University. Today I'm going to present our work on efficient concolic execution of WebAssembly by compilation and snapshot reuse. And this work is done in collaboration with Alex from New York University and my PhD advisor, Guannan. WebAssembly is a low-level IR that can be run in various environments. It has been widely adopted in many important areas. More interestingly, it has a formal, well-defined semantics. It's interesting and important because it brings new opportunities for the semantics-based applications, such as semantics-based testing, static analysis, and verification. And today, we're focused on the semantics-based testing technique called concolic execution. In this work, we present an efficient WebAssembly concolic execution engine that can generate test cases to find bugs in WebAssembly program. And its performance is achieved by two optimizations. First is that it has no interpretation overhead. And the second is that it avoids the duplicated execution during the concolic execution. These two optimizations cannot be applied together in the previous works. And in the rest of this talk, I will discuss how to achieve these two optimizations at the same time. Concolic execution is a technique based on symbolic execution. Let's see what symbolic execution is with an example. Then we come back to the concolic execution. On the left is an example program that has two variables, x and y, which are assigned from two inputs. And it has an assertion error at its third branch. On the right side is all possible execution paths of it. We can feed this program to a symbolic executor and ask it to generate a test case that can reach the assertion error. First, the symbolic executor will replace the input of the program with symbols. Instead of executing the program with concrete semantics, it uses these symbols to execute symbolic semantics. During the symbolic execution, it will collect a set of constraints represented by these symbols. These constraints are called path conditions. They represent the condition of input that must be satisfied to reach a particular path. For example, the path conditions of the leftmost path is x less than or equal than 0. Because to reach here, the first if condition must be true. Unlike concrete execution, symbolic execution can execute multiple paths of the program at the same time, just by executing the symbolic semantics for different paths and collecting the path condition for each of them. And we say symbolic execution is exploring the program. And we can see that the explored path of the symbolic execution naturally forms a tree structure called exploration tree. And using a constraint solver to solve the path condition can produce an input that reaches the path. For example, for the path that contains the assertion error, solving its path condition can generate an input that triggers the error. That's the basic idea of symbolic execution. However, there's a scenario which is challenging for symbolic execution. If the program contains some very complex logic at the beginning, right now you only want to focus on the deeper places of the program, and using symbolic execution found the bugs in there. The symbolic executor will spend a long time at the beginning of the program exploring the complex logic in there before reaching the part you really care about. To help the symbolic execution to reach the deeper path earlier, concolic execution comes. Concolic execution can be seen as a special exploration strategy of symbolic execution. It executes symbolic semantics on different paths, just like symbolic execution. But in concolic execution, the exploration is guided by concrete execution. That is why it's called concolic execution, because it needs to execute both concrete and symbolic semantics at the same time. Let's go back to the previous example to see how it works. First, concolic execution will start the program with a concrete input. Then it will execute the concrete and symbolic semantics at the same time. And in practice, this concrete input can generated by a fuzzing tool. So it can start the exploration from a very deep path at the beginning. After the first run and no error was triggered, it will keep exploring the program with different input. When it catches an error in the program, like our example here, it successfully generated a test case that triggers the bug, which is just the current concrete input. That's the basic idea of Concolic execution. It can reach deeper places earlier just by starting the exploration with the concrete input that reaches the deeper places. There is an interesting thing that you may have noticed. During the Concolic execution, different paths are sharing a common subpath. For example, we have explored the first path, which is marked in green. And now we want to use a different input to explore a new path, which is marked in blue. We can see that the blue path and the green path is sharing a common prefix. And the execution of this common prefix is duplicated. When the execution goes deeper, the cost of such re-execution could be significant. Ideally, to avoid such re-execution, when exploring a new path, we should start from the end of the common prefix, rather than start from the beginning of the program. To do so, we need to save a snapshot of the program, where a snapshot is the control information and the symbolic states at the branch points. When Concolic execution wants to explore a new path, it can reuse the snapshot, resume the execution from the snapshot, and avoid re-executing the common prefix. And this reuse mechanism is called snapshot reuse. That's the basic idea of Concolic execution and its snapshot reuse optimization. For the implementation of Concolic execution, there are two main patterns for the mainstream works. The first one is the interpretation-based approach, and another one is instrumentation-based approach. And they both have their own pros and cons. Let's see them one by one. Since the Concolic execution is guided by concrete execution, a straightforward way to implement it is to base the implementation on an existing interpreter. Inserting those extra symbolic operations into an existing interpreter to turn it into a Concolic interpreter. Running this Concolic interpreter will not only get the concrete output, but also the path conditions collected during the execution. For example, the work Wasm in 2022 eCoop do Concolic execution for WebAssembly by inserting extra symbolic operations into WebAssembly official interpreter. For this approach, snapshot reuse is not a challenge because the control information and the states are fully managed by an interpreter. However, for the interpretation-based approach, there is an inherent performance limitation. That is the interpretation overhead of dispatching on different instructions. It's a well-known limitation of interpretation, and lots of work have shown that this overhead could be significant in practice. A solution to the interpretation overhead is implementing Concolic execution by instrumentation. Instrumentation is a program transformation technique that inserts extra operations into the program to collect hidden information of the program during its execution. If we treat the path conditions as the hidden information we want to collect, we can build a Concolic executor via instrumentation. Here is an example for the instrumentation for our WAM. We can see that the symbolic operations have been inserted at the head of the program. When the execution reached here, these symbolic operations will be executed first, then comes to the original concrete instructions. In this way, we achieved Concolic execution for our WAM. This is not a WebAssembly example, but it's not hard to apply the same idea to the WebAssembly, Concolic execution. If we build Concolic execution in this way, it will have no interpretation overhead. However, at the instrumentation time, the program doesn't capture the control information, therefore disables the snapshot reuse optimization we just talked about, because snapshot is created from the control. That is why we want to have a new approach that can combine the best of these two words. First, it should have no interpretation overhead, like instrumentation-based approach. And it should be able to do snapshot reuse optimization to avoid re-executing the common prefix, like interpretation-based approach. To achieve these two goals at the same time, our idea is compiling the WebAssembly Concolic semantics to a low-level program language with continuations. To capture the control information, our approach is based on the CPS semantics of WebAssembly, which was proposed in our previous work on TFP'25. To do concolic execution, we first insert extra symbolic operations to CPS interpreter to get a concolic interpreter. To eliminate the interpretation overhead, we apply the partial evaluation to the staged version of CPS concolic interpreter to generate C++ code. Finally, combining the generated code with the runtime of symbolic operations, we can get an executable concolic program. This concolic program performs both concrete and symbolic semantics and uses captured control information to achieve snapshot reuse. Now let's get into some technical detail of our approach. Our compilation is based on a program transformation technique called partial evaluation. It takes two inputs, a staged program P and P's input that can be known in advance, called static input. The output of partial evaluation is called a residual program. In residual program, there is no more computation that only depends on the static input because they have been pre-computed during the partial evaluation. Staged program is just a normal program with some binding time annotations, which is just a type of annotation indicates whether an expression depends on static input or dynamic input. The lightweight modular staging, LMS, is a partial evaluation framework embedded in Scala. We use LMS to apply the idea of partial evaluation. Let's see how LMS works with a simple example. Here on the left is a function that computes b to the power of x. When the exponent x is known in advance, we can specialize this function respect to x. So we mark b as dynamic input with wrap and leave x as it is. In this way, if we apply partial evaluation to a specific x, for example, if x equals to 2, then we can get a specialized version of power function in C++ that only takes b as input and calculates b squared. Remind that the residual program is in C++. This is a powerful feature of LMS. It can specialize the staged program into different languages. The application of partial evaluation can be very flexible. If we apply this technique to an interpreter, partially evaluating the interpreter with the source code as the static input, we can get an executable program as a residual program. This observation is also known as the first filter mirror projection. And we will realize this observation to implement our Concolic compiler, partially evaluating a Concolic interpreter with the WebAssembly source code to get an executable Concolic program. Here is the outline of the staged Concolic interpreter. It's a staged version of a Concolic interpreter with several parts are marked as wrap, which represents the dynamic computations. First, we use function without parameters to represent continuations. The eval function contains the core logic of the interpreter. It takes a list of instructions, a continuation, and a trail as parameters. Based on this captured continuation, we can create a snapshot further. And the trail is a list of next stage continuation, which acts as local jumping tables. On the other hand, the instruction list and the trail parameter are not marked as wrap. So the computation based on them will only exist in the current stage. For instance, the instruction dispatching expression in the eval's body are all happening in the current stage. So they will not occur in the generated code. In other words, the interpretation overhead is eliminated. Here is the compilation for some simple instructions. For the constant instruction, we push a constant to both concrete stack and the symbolic stack. Correspondingly, in the generated code, there will be 2 push operations. And for the BR instruction, which stands for branch, we enter the continuation stored in the current trail. And in the generated code, there will be a function call to the continuation function, corresponding to the label 1, which is x3 here. And another interesting example is the compilation of if instruction, because it shows how we utilize the control to achieve snapshot reuse. Here on the left is an example of if instruction, and on the right is the generated code of it. The generated program first pops the value that represents the condition from the concrete stack and the symbolic stack, and updates the exploration tree with the symbolic condition. And then use the concrete condition to decide which branch to go. If we enter the true branch, first we create a snapshot with the fourth branch's continuation and current symbolic states. Then we expand the exploration tree to the true branch and store the snapshot into the tree. Finally, we enter the continuation of the true branch. For the fourth branch, we just do the similar things. Create a snapshot, expand the tree, store the snapshot, and enter the continuation. That's the basic idea of implementation. And here's a preliminary evaluation of our Concolic execution engine. We compared our engine with Wasm, which is a Concolic interpreter for WebAssembly in OCaml. The improvement by compilation is significant. On different configuration, our engine can achieve 6 to 15 times speed up compared to Wasm. Once again, it's still a preliminary evaluation. The benchmarks are small programs that only last for a few seconds. And we are working on more comprehensive evaluation on bigger benchmarks. To summarize, we have presented a WebAssembly Concolic execution engine that eliminates interpretation overhead by compilation to C++, and it avoids the re-execution via snapshot reuse. We built our compiler starting from a definitional CPS interpreter and realized partial evaluation to simplify the compilation. To the best of our knowledge, our tool is the first Concolic execution engine that can achieve both no interpretation overhead and snapshot reuse optimization. That's all of my talk. Our source code is available at GitHub, and I'm happy to take any questions, comments, or suggestions. Thank you for your attention.
So this is a really cool work, by the way.
Thank you.
So it sounds like you kind of hack an interpreter to do the snapshot for you. So it's this combination of doing both interpretation-based and instrumentation-based. So is that correct?
It's correct, but we not based on the WebAssembly official interpreter. We developed our own Concolic interpreter, and based on that, to do the snapshot and compilation.
So do you think that you would have a lot of, I guess there would be a lot of overhead if you do, because you could do snapshots inside instrumentation, right?
It's hard to do that because
be higher overhead.
You mean do snapshot in instrumentation?
Yeah, like do you think that it would be possible to do like the snapshots totally in instrumentation? It would be higher overhead, but you wouldn't have to have this custom interpreter.
I think it's hard to do that because usually at the instrumentation, the program doesn't capture the control. So,
well, you could have like shadow memory and shadow stack and stuff to like.
You mean copy that would be a lot of
It would
hack.
be high overhead, but like, do you think that it would be so high overhead that it would be prohibitive?
That is not just overhead, but it's also not semantic based. So I'm not sure if I'm answering your question, but our work is based on instrumentation on an interpreter, which is semantic based, so we can ensure the correctness during all the time. But if you want to do that via instrumentation, I think it's hard to ensure the correctness.
Yeah. Okay, we can talk more offline.
Yeah, of course.
Yeah, cool.
So, this is very foreign to me, so the question might be nonsensical, but I'm a little bit surprised that you start from a CPS interpreter, because one of the things that WebAssembly has, it has this sort of structured control flow that does give you this information. And then you seem to sort of immediately throw it away, because the CPS interpreter kind of forgets all of that structure in a sense.
WebAssembly's structured control flow only captures the local control information. And what we want to capture here is the full control information. So like what we are going to do after the function return. So.
Okay. Okay, thank you.
Thank you.
Thanks for the impressive talk.
Thank you.
I know when I used to have some similar things on LLVM, I'm not pretty sure it's the same thing or what was the difference. So what's the gap here between the LLVM stuff and here for WebAssembly?
You mean what work on LLVM?
I mean, Guannan used to have the version on VM, right? Is it the same thing or?
The essential idea are similar. It's about eliminating the interpretation overhead and utilize the control of the program. So it's definitely not the same thing because the language is different. But I think the basic idea is really similar. Yeah.
Nice. Thanks.
Great. Let's thank the speaker one last time.
Thank you.